Hello, Math 141. Welcome to episode 1 of recitation here this summer. Today we are going to be putting the fun in function. Ha ha ha, what a clever wordplay. You can see this M141SU20 little abbreviation at the beginning. I think that I'm going to put that at the beginning of all of my videos, just to make it clear what this is for. I don't know if I'm going to put other videos on this channel someday or not, but in any case, it will help us organize so you know exactly which videos are for you if I decide to branch out and go a little crazy. So episode 1 today, again, putting the fun in function. We're going to talk about sections 1.1, 1.2, and 1.3. We're not going to necessarily go in any order. We're really just going to pick some problems from throughout the homework on these 3 sections. And we'll jump around a little bit and do a bunch of them. I did get one request, so there will be one requested problem, but all the others are going to be ones which I've looked at and feel are pretty good practice problems, pretty good example problems to work through. So the first section looks at functions and their graphs. So what is a function and what does the graph correspond to? Section 1.2 then looks at how we can combine functions and how we can shift and scale those graphs. For example, how do changes in the function change the geometry of the graph? And then section 1.3 looks at everybody's favorite, the good old-fashioned trig functions. I think that those are ones that people are a little bit scared of at first. I'll admit I'm a little bit scared of them sometimes, but I think that with time you will come to see that deep down they are really wonderful, wonderful people. I do apologize again for getting this video out a little bit late. I had some technical issues, but now the math department has hooked me up with an iPad to borrow for the summer. So shout out to the U of SC math department. So we should be ready to rock and roll. So without further ado, why don't we go ahead and do some problems, do some math here. And I want to start with the very first homework problem. So when I'm number problems like this, that's generally going to correspond to that problem on the corresponding homework. So problem 1 on this homework says to find the domain and range of the function. I hope that everybody can read my handwriting. If not, please just shoot me an email. I don't know, ask me something in the comments, whatever. So f of x here is negative x squared plus 2x minus 8. Okay, so we want to find the domain and range of this function. So I think the best place to start would be to remind ourselves, well, what the heck do those things even mean? So the domain, you'll recall, and these are going to be somewhat informal definitions, but basically this is how you want to think about it. So the domain is going to be all possible x values. I'm going to say which we may legally, I'll explain what I mean there in a second, plug in. Plug in. I'll put legally in quotes. So what I mean here, all possible x values that we can legally put in, well, sometimes, for example, we might have something where if I plug in a certain value of x, all of a sudden I'm dividing by 0, and then the math cops are going to be after us because we know that we can't do that. Similarly, if we're looking under a square root, we're always going to want our things to be greater than or equal to 0, because in the real numbers, negatives have no square roots. We'll go through an example in a little bit, which tells us, in which we'll see some of this in action a little bit more. So if we jump to our specific function here, f of x equals negative x squared plus 2x minus 8, well, let me ask you, what possible x values can we legally plug into this thing? And usually, whenever we ask that question, really what we want to ask is, so what we really are we're kind of asking the opposite question. What can't we plug in? Because usually you can plug in most things. So really the question here is, what can't we plug in? Is there anything that we can plug in that's going to break this thing? And the answer in this case is no. Nothing. There's nothing that we can plug in which will break it, right? Because no matter what I plug in, I can always, this expression here, negative x squared plus 2x minus 8, is going to make sense. So the domain in this case is going to be all real numbers, and we write that using the interval negative infinity to positive infinity. Infinity always gets an open parenthesis because we cannot include infinity technically. Okay. So again, this is just all real numbers. This is just, excuse me, our fancy interval way of writing all real numbers. Okay, so that's our domain. That's not so bad in this case. Sometimes it can be more complicated, but in this case, that's fairly straightforward. Okay, so let's look at the range. Let's do range in red because alliteration. So the range then is going to be all possible outputs of the function, So in this case, really what we're asking is, what possible values can this guy, this negative x squared plus 2x minus 8, what possible values can that take on? So I'll write that here. What we're asking is what possible values can negative x squared, what was it, plus 2x? Yeah, plus 2x minus 8 take on. Okay, so that's really what we want to know here. At first glance, it might seem like all of them, right? It kind of seems like, how could there be anything which doesn't get hit by this? Sometimes you can do these things algebraically, and you can find some answers that way. But in this case, algebraically, I just don't see very much that we can do to really help us answer this thing. So I think what we want to do here, so algebra, maybe algebra could help us a little bit, but it's not super helpful here. But what is going to be helpful here, and this is going to be a pretty common technique in finding the range, is let's draw a picture. Draw a picture. And that can oftentimes be more illuminating than fancy equations or algebra. Now, I'm not very good at drawing pictures, but I'm going to do my best here. So let me plot my x and y. Look at that. Look at how straight that is. So my function here, negative x squared plus 2x minus 8. Well, this negative, so this negative here indicates, well, actually, let me start with the 2. This x squared here indicates that it's going to be a parabola. Okay, it's going to be some sort of parabola. And the negative here, that then tells me that it's downward. So it's going to look something like this. Okay, so the negative out front of the x means it's going to open down. And the square here tells me that it's going to be some sort of parabola. So I don't know exactly what it's going to look like, but I can draw a sketch. It's going to look something like that, maybe. I don't know. Again, we don't need super specifics right now. What's important is that it's a parabola that's opening down. So what we can see is, so I've got this vertex here, and I can get every y value below, so all y values below that vertex, all y values below vertex are going to be included in our range, are in the range. Because, for example, eventually this thing is going to go down to like negative 1 million, right? Negative 1 million. There's going to be some point on this curve with the x-coordinate negative 1 million, or excuse me, with the y-coordinate negative 1 million, right? So everything below the vertex, there's going to be some some point whose y-coordinate, so let me write this in words, because I think so for all y-coordinates below vertex, there is some point on curve, with that y-coordinate. So that is how we know that all the y values below the vertex are in the range. So what we need to do is find vertex. So we need to find that upper bound. So we must find the vertex. And again, this is where drawing pictures, oops, I didn't mean to do that, is going to help us out a little bit. So what I'm going to do is I'm going to make a little table. So in the left column, let's put x. In the right-hand column, let's put y. Okay, so y, which is going to be equal to negative x squared plus 2x minus 8, was it? Yeah, minus 8. Okay. And we're going to plug in a few x values to see if we can figure out where that curve is. We're going to try and find a few points. So let's start at, say, x equals, let's go from -2 to +2, -2, -1, 0, 1, 2. All right, we're going to plug these guys into our formula here. I'm going to do this kind of quickly, but you guys can, I encourage you to check these yourself. So if x is -2, then y is -16. All that I'm doing is plugging -2 in for x here. If I plug in -1, then I have, let me see, I have -1 minus 2 is -3 minus 11, I think. If I plug in 0, I just have -8. If I plug in 1, -1 plus 2 is 1, so minus 8 is -7. Now if I plug in 2, then I have -4 plus 4, -8. Okay. And so my picture, now I can see, look at this, the y values are decreasing. So they are decreasing until, so, y values increasing. Then it hits this -7 and it starts decreasing again. Right? So -16, -11, -8, -7, it's getting bigger. But then it starts to get smaller again. It goes from -7 to -8. So our picture is going to look, and I'm going to just do a quick sketch here. But at x equals 1 is where it starts to go down again. So it's going to look something like that maybe. And this is our point 1, -7. And so what we conclude is that everything below this -7 is included in our range. So our range is going to be, we include -7 here because we are able to get it. Excuse me, so we're going to start at -infinity because we get everything down here. And we're going to go until we get to -7, and we're going to include that -7. Okay, and that gives us our range, because again, those are all of the y values that are hit by this picture. So as you can probably see from that first example, a lot of times finding the range is actually more difficult than finding the domain. But other times it's backwards. It really depends. Okay, so that gives us problem 1. Why don't we look at problem 4 now? So let's jump to problem 4. In this one, we're just going to find the domain because we've got a more complicated function here. Find the domain of the following function. A lot of times I'm going to do problems on here that are slight variations of the homework problems. Like, I don't remember if that first one was actually verbatim the homework problem. This one I know for a fact is not verbatim the homework problem. However, it's very similar. So the idea is that you can use the ideas which I show you here to help you with the exact problems. And again, if you ask for a specific problem, I would be glad to do that specific problem. Okay, so we want to find the domain of this function. So again, let's scroll back up to our definition of domain to remind ourselves. So we want all possible x values which we may legally plug into the function. Okay? All possible x values which we can legally plug into this. So the question that we need to ask is, what problems might we run into? And I see two of them here. What problems must, I'm going to say this, well, what problems must we avoid? And there are two problems here, which are going to be which are going to be very common problems that you need to look out for whenever finding the domain of a function. So first, where did my little, here we go. So first, I cannot have radicals, so can't have negatives under a square root, right? Because like we said earlier, well, I can't take the square root of a negative number, so that wouldn't make sense, and the function would break. So in this case, what does that mean? Well, that means that x squared minus 25 must be greater than or equal to 0. If that is not true, then I'm going to be taking the square root of a negative number, and math is going to break on us. So we know that x squared minus 25 must be greater than or equal to 0. Well, this is the same as saying x squared must be greater than or equal to 25, just by adding this 25 over to both sides. And now, if I take the square root of both sides, we need to be a little bit careful here. Because if x is say negative 6, so let's make a comment here. So if x equals negative 6, well then x squared equals 36, which is certainly greater than or equal to 25. So we need to, so this thing here, this x squared greater than or equal to 25, this implies that the absolute value of x is greater than or equal to 5. Okay, this doesn't just mean that x is greater than or equal to 5, because, again, we also have to consider these negative cases below negative 5. Okay, so we know that the absolute value of x must be greater than or equal to 5. Well, this is the same as saying, if we prefer, that x is less than, what on earth was that as a z? Less than or equal to negative 5, or x is greater than or equal to positive 5. So that's one thing that we need to take into account. That's one way which restricts our domain. Another problem which we might have in this case, anytime that we have a fraction with variables in the denominator, we cannot divide by 0. So can't divide by 0, right? Because again, that is totally illegal. If you're looking for a fun time for a few minutes, go ahead, if you have an iPhone, and ask Siri what 0 divided by 0 is, and you'll get a good laugh. So in this case, our denominator is 4 minus root x squared minus 25. And I need this thing to just not be equal to 0. It can be bigger than 0. It can be smaller than 0, right? In this case, we couldn't have it be smaller than 0 with the negatives, with the radical. Here, it's okay if it's smaller. It's okay if our denominator is smaller than 0. It just cannot be on the nose equal to 0. So this is the condition that we must satisfy. This 4 minus x squared minus 25, not equal to 0. And just like before, we're going to algebraically solve this to find a nice condition on x. Okay, so if I subtract 4 from both sides, actually let me do this. Let me add the square root to both sides. So that means that 4 is not equal to x squared minus 25. If I square both sides, that means that 16 is not equal to x squared minus 25. And now if I add 25 to both sides, that means that x squared is not equal to 41, which means that plus or minus root 41 is not equal to x. Right? Okay, so now we've got these conditions here. So I need x to not be plus or, the plus or minus needs to be in my box. X cannot be equal to plus or minus root 41. And I also need x to be less than or equal to negative 5 or greater than or equal to positive 5. Now, the question which you should be asking is, well, is plus or minus root 41, we'll just say it this way, is root 41 greater than or equal to 5? Well, I don't know exactly what root 41 is, but I do know that root 41 lives somewhere between 6 and 7. How do I know this? Well, 6 squared is 36, right? So squared equals 36, and 7 squared equals 49. So therefore, the square root of 41 must be somewhere between these two. So what does this mean? So yes, to my question, which means that we must exclude these points from our interval. Exclude plus or minus root 41 from domain. Which means then we now have enough information. So our domain is, well, at the left, we can get everything below negative root 41, but then we need to exclude negative root 41, right? Because if x is negative root 41, things break. And then I can also take the things between negative root 41 and negative 5. Okay, again, that goes back to these conditions here. Okay, so x is less than or equal to negative 5. That's all well and good, except for negative root 41. It's okay if x is equal to negative 5, so we are going to include that one. Now, if I look at the things between negative 5 and positive 5, those things we all excluded because those things are not less than or equal to negative 5 or greater than or equal to positive 5. So now we're just going to jump on up to positive 5, and we'll go until positive root 41, not including root 41. And finally, we will then take everything bigger than root 41 all the way up until infinity. So this is our domain. It's a little bit more complicated looking, but that is what it looks like here. So what are the two? There are really two takeaways from this one, which I hope we demonstrated. So there are two takeaways. And those were really those two conditions that we checked. So one, so we can't have negatives under a radical. Now you have to be very careful with this under square root, but you have to take caution because I can have a negative under a cubed root, for example, because the cubed root of negative 1 does exist. In fact, it's equal to negative 1. So we are allowed to have negatives under cubed roots, but not under square roots. So that's one thing that restricts our domain. And the other thing which restricts our domain is we can't divide by 0. Okay. So those were the two things which we used in this case to determine our domain. Another thing which I'll point out, and I didn't do it here, but it is oftentimes helpful to draw a picture, to draw a number line. As you are doing this, helpful, not helpful. Help, help, I need somebody. Helpful to draw a number line to organize yourself. Number line to organize. Okay. So that gives us problem 4. Again, that was a slight variation on problem 4, but you should be able to use those same ideas whenever you are doing it on your own. So next up, next one is another fun one. So next I want to do problem 21. And I think in this one I am doing the exact problem. Oops. So this one, let me pull it up real quick actually. 21. Oh, hang on a second. It kicked me out of my math lab. And I had to sign in again. Here we go. Okay. So there are 2 parts to this one. Well, 3 parts actually. So for the given functions, so A, we're told to write a formula for f composed with g. For f composed with g. Okay, we'll review kind of what that means in a second. And we'll be given a function f and g. And then find the domain. Oh, actually, excuse me, hang on. We want to find a formula for f composed with g and g composed with f. Okay, those are 2 different things, and we need to be careful. We'll see in a minute how those 2 are different. Find the domain of each. Find the domain of each, and by that I mean of f composed with g and of g composed with f. That's what I mean there. And then C, find the range of each. Okay. So those are the instructions. Our functions, let's put them in red. So f of x is root x plus 3. And g of x equals 1 over x. Okay, so those are our functions. So let's get going with part A. And let's find f composed with g first. So remember, f composed with g, this fancy little circle here, that's just a fancy way of saying f of g of x. And the way that we're going to do these composition problems is we're going to start from the inside and work our way outside. So in this case, g of x, well, g of x is just 1 over x, right? That's just from the definition up here. G of x equals 1 over x. So this is f of 1 over x. And I'm going to step aside here for a minute because that might look a little bit scary. But if I asked you to find, say, f of 2, you know how to do that. All that you do is you take your formula for f and you plug in 2, right? You plug in 2 for x. So f of 2 is the square root of 2 plus 3 because f of x is square root of x plus 3. So f of 1 over x looks big, bad, and scary. But all that we do is the exact same thing that we did for, say, f of 2. And it's just the square root of, well, I'm going to replace x with 1 over x. So I have 1 over x plus 3. Square root of 1 over x plus 3. And this is f composed with g of x. Okay, maybe I should make that more clear. That's 1 over x. That is 1 over x plus 3. It kind of looked like a 4. All right, so that is what f composed with g is. Now, why don't we go ahead and let's try and find the domain of f composed with. So let's jump to part B for this function. So find domain of, well, in this case, our function is, of f composed with g. Okay. So our function is 1 over x plus 3. Okay, and so there are kind of the same two things that we observed in the last problem are taking place here. So our first observation is that x can certainly not be 0 because we can't divide by 0. Can't divide by 0. Right here I have a 1 over x under this radical. So if x was 0, then I'd be dividing by 0, and all chaos would break loose in the mathematical kingdom. So that's my first observation, is that x certainly cannot be equal to 0. The second thing which we need to be true is that I need 1 over x plus 3 to be greater than or equal to 0. This is because, as we talked about with the previous problem, I cannot have something negative under a radical. So that gives me this 1 over x plus 3 must be greater than or equal to 0 condition. Now let's try and figure out what this means. Well, first of all, notice x greater than 0 are always going to work. All good, all right. Right? Because if that is true, then 1 over x is greater than 0. So 1 over x is greater than 0. Which means that 1 over x plus 3 is certainly greater than 0. So that's why this is always going to work for x greater than 0. So now the question is, what about the smaller x? What about x less than 0? Which ones of those can we put in our domain? Right, and we know that x equals 0. We already know we can't have that. So now we just need to figure out which ones that are smaller than 0 work. So 1 over x plus 3 greater than 0. Well, this is the same thing as 1 over x is greater than or equal to negative 3. Now, we have to be careful here. So I'm going to multiply both sides of this by x. On the left-hand side, I'll get 1. On the right-hand side, I'll get minus 3x. But I need to flip the sign. So flip sign, because now we are assuming that x is less than 0. We are now investigating the cases when x is less than 0. And whenever we multiply by both sides of an inequality by a negative sign, we need to flip the inequality. Okay, that would be a good algebra fact to review if that's something that maybe isn't coming to you, if that doesn't ring a bell. Okay, so this 1 over x greater than or equal to negative 3 becomes 1 is less than or equal to negative 3x. Now dividing both sides by negative 3, well, again, I'm going to have to flip the sign because negative 3 is negative, which means that 1 over negative 3 is greater than or equal to x, or in other words, x is less than or equal to negative 1/3. This corresponds to the interval negative infinity to negative 1/3. And we are closing it at negative 1/3 because we are allowed to include that point. Okay? So that gives us our domain. So our domain then, well, we have this piece first. Now we're going to piece everything together. We go from negative infinity to negative 1/3. And then in the positives, we already said that we can have anything greater than 0. So then we're going to include from 0 to infinity. We're not going to include 0 because, as we've observed right away, we cannot include x equals 0. So this gives us our domain. Okay? Let's look at the range then. So see the range of f composed with g. Okay, and just as a reminder, f composed with g of x, well, that was the square root of 1 over x plus 3 equals root 1 over x plus 3. Okay. Well, we can see pretty much right away that we can get anything positive. Everything here is always going to be positive, right? So always positive. So we're going to get all the positives. But how about 0? How about 0? The reason that we're always going to get the positives is because we don't have a negative out front here, right? Now we do, because I just made a tiny little dot, but now we don't. Okay. Well, can we get 0? Well, notice if I plug in x equals negative 1/3, well then this becomes the square root of negative 3 plus 3. If I just plug this in, equals 0, because negative 3 plus 3 equals 0. So sure enough, 0 is in our range because we included negative 1/3 in the domain. And whenever we plug that in, that gives us 0. So this means that 0 is in our domain, or excuse me, in our range rather, in our range, which means that the range is just going to be all non-negative numbers. So from 0 to infinity closed at 0. All right. So I think that what I will do now is I will leave. Yeah. So I'm going to leave f g composed with f as an exercise for you. Exercise for you. I'll put a smiley face so that you don't hate me. See, I'm happy. You're happy. You're not sad. You're going to follow the exact same procedure we followed here, but you'll notice it's going to look a little bit different because rather than f of g of x, you're going to have, rather than f of g of x, you'll have g of f of x. And I'll go ahead and get you started. F of x, so this is g of, well, f of x was, here. It was root x plus 3. So this is g of root x plus 3. And then I will leave it to you to determine what this is. All right. So that wraps up our work here in problem 21. A little bit left for you. Let's jump and do problem 29. So this one, we're going to talk through a little bit of geometry. Truthfully, I don't know. Maybe you guys are better at this than I am. Geometry is not my strong suit. I have a hard time visualizing things. So this is definitely good practice for me as well. So it says graph the following function. So I'm going to abbreviate here. Graph the function by starting with the graph of y equals root x, and applying transformations. I don't think we'll actually graph it here, but I'm going to talk through at least what the different transformations look like. So the function which we're given is y equals negative root 5x plus 6. And what we're supposed to do is we're supposed to relate this back to the y equals root x graph and see how these different changes affect things. And in fact, there's actually a little sentence here in words, which with little fill in the blanks on the actual MyMathLab problem. So there are three kind of transformations going on here. The one is we've got this 5 out front of the x. The second thing is that we've got this plus 6 here. And the other thing that we have is the negative out front. Okay, so those are kind of the three changes that we've made to the graph of y equals root x. So what we're going to do to start is we're going to rewrite this. So, oh, go away. What? No. Okay, here we go. So rewrite. Okay. Rewrite as y equals negative. And now what I'm going to do, I'm going to pull a 5 out of both things, out of both sides. Pull a 5 out under here. And rewrite this as x plus 6 over 5. All right. So now this makes it a little bit easier to visualize. So the first thing that we're doing, so this, first we notice, so the first thing that I see is that x plus 6/5 shifts the graph 6/5 units left. Okay. It's kind of counterintuitive how plus 6/5 moves us in the negative x direction, right? It moves us left. It kind of feels like it should move us in the opposite direction. But in any case, this is how it works. That's a tricky thing to watch out for, that kind of common mistake. I had the hardest time getting that through my head when I learned this stuff the first time. That doing plus 6/5 actually moves it in the negative direction. The way that I finally made sense of it was just to think about geometrically. If you plug in a few points, then you start to see what happens. So I encourage you, if some of these transformations aren't making sense to you, start with a somewhat simple graph and plug in a few points and see what happens. And hopefully then it can click a little bit more for you. Okay, now the second thing that we're noticing is this 5 out front. So 5 out front compresses the graph, that's an R, compresses graph horizontally because it's in the x direction, because it's compressing here, it's right here with the x. Compresses the graph horizontally in the x direction, horizontally by a factor of 5. Again, it's kind of counterintuitive that multiplying by 5 compresses the graph, but I think if you plug in some points, that might be helpful for you to help see why. And third, I don't know why I wrote C, 1, 2, C4, 1. So the third thing that I notice, this negative out front, well, that's just going to flip it over the x-axis. So the negative out front flips over the x-axis, And the way that I would think about this is as follows. Let's say that without the negative, if we ignore the negative for a second, then everything else here gives me like a 1. Well, then I would get y equals 1, but putting the negative out front means that instead of spitting out a 1, it's going to spit out a negative 1. So it's just going to flip everything over the x-axis. Okay, so those are what these three transformations do in this case. It is very helpful to rewrite it like this. I think this is probably one of the key takeaways from this problem, and one of the reasons that I wanted to show it. Writing it like this and getting the x with the important part here is that now the coefficient for the x is a 1. Right? Inside here there's a 1 in front of that x. That is what allows us to reach this first conclusion. Then the 5 out front gives us the second conclusion, and then the negative gives us the third. Okay. So I've got 2 more problems lined up for us here, one of which comes from the homework, and one of which was the requested problem, which is actually not from the homework. So problem 38 on the homework. So we're told to find the function value, and I'm actually twisting this one a little bit too. The homework problem asks for sine, but I am going to replace that with cosine. Cosine squared of 9 pi over 8. All right, so what's tricky about this? I think this is a very tricky problem. It took me quite a few minutes to figure it out. So don't feel bad if you've struggled with it. You shouldn't feel bad if you struggle with any of them, but this one in particular I found to be difficult. So I don't know anything about cosine with things of pi over 8. Like this 8 is what's throwing me off. Like I know cosine of pi over 4, pi over 3, pi over 6, pi over 2, but I don't know anything about stuff with an 8 in the denominator. The first thing that I try to do is I try to use angle addition identities. Okay, so things like cosine of a plus b, cosine of a minus b, things like that. Angle addition formulas. And so I tried to toy around with this. So how can I get an 8 in the denominator using things I know? How can I get 8 in denominator using things I know? By things I know, I mean those pi over 6, pi over 4, pi over 3, etc. So I tried that for a while. I tried to toy around with it with some algebra to make it work. And then I had to come to the sad realization that I could not do that. And then I cried a little bit, as per usual, as I'm sure you all can relate to. I'm kidding, I didn't actually cry. I picked myself up and I said, okay, Bailey, what else can I do? How else can I be clever to work around that and solve this problem? So then I made the observation. So unfortunately, path 1 did not work out. The second thing which I tried, well, really, it's more, I started with this observation. I observed, well, 9 pi over 8, that's just 9 pi over 4 times a half. Right, so I don't know 9 pi over 8, but I do know that it's 1/2 of something which I do know. So then the question became, do I know any half angle identities? Do I know half angle identities? right? Like, do I know anything about, if I know cosine theta, can I use that to find cosine theta over 2? Because that's really, if I could find some formula in terms of cosine 9 pi over 4, I could work with that. Whoops. Sadly, I don't know any of those off the top of my head. However, but there is one formula that stuck out to me. I do know that cosine squared of theta is equal to 1 plus cosine of 2 theta over 2. This is a very important formula. Put a star here. You should definitely know that one. This is a formula, so I've been a Calc 2 TA the last 2 semesters, and this is a formula which we use a lot in that class. So this would definitely be a good one to familiarize yourself with. There's a similar identity for sine squared, so I would encourage you to get familiar with that one as well. Now, how is this helpful? This is helpful because what I see is that I've got 2 theta here and 1 theta here. So this angle here, this 2 theta, is twice as big as this angle. And I know something about, and going back to our original, 9 pi over 4 is just 9 pi over 4 is twice as big as 9 pi over 8. So there is a relationship here that I can exploit. That sounds bad. I'm going to exploit you, relationship. Don't exploit your personal relationships, please. Just your mathematical ones. So here's what I'm going to do to make this a little bit easier to see. Well, actually, no, I don't even need to do that. Yeah, okay. I don't need to do that. I was actually going to make this a bit more complicated than I need to, because that's how I did it whenever I did this problem. But actually, I can do it more simply. So if I let theta be 9 pi over 8, well, then this tells me that cosine squared of 9 pi over 8 is equal to 1 plus cosine. All right, well, 2 times 9 pi over 8, that's just 9 pi over 4 over 2. Just using this identity with theta equals 9 pi over 8. And so now, excuse me. So now if I can just find cosine of 9 pi over 4, then I'm done. And how do I find that? Well, I'm going to draw me a circle. 9 pi over 4, so that's going to take me 9 pi over 4. Well, that's 2 pi, and that gives me to 8 pi over 4. And I have one more pi over 4 left over, so that gets me here. So this is pi over 4. And cosine of pi over 4, so cosine 9 pi over 4, that's just cosine of pi over 4. And that is root 2 over 2. I saw in one of Mackenzie's videos, she said that if you don't know your unit circle, it's going to come back and get you in the butt. And she is absolutely right. That's going to be so important for you both in this class and if you continue on in calculus moving forward. So I definitely encourage you, take some time to learn the unit circle. I think Mackenzie showed you a fun way. I have my own little trick which I use, which is pretty much the same as hers. It's very similar, but a little bit different. If you want to Google something to help you memorize it, that's fine, but find something that works for you. You don't have to use her way or my way, just some way that works for you. And so, now that we have this information, I can conclude that cosine squared of 9 pi over 8 equals 1 plus cosine of 9 pi over 4 is root 2 over 2. All of that over 2. And you could simplify this if you wanted to, but I'm not going to work through that here. All right. So this I found to be one of the trickier problems on the homework. So again, if you were struggling with it, Don't feel bad at all. Don't ever feel bad about struggling with any homework problem. But like I said, this one in particular I found to be challenging. Finally, let's wrap up with one of the problems from class, from Mackenzie's video. This is one that she did at the end of her 1.3 video, which someone wanted to see in a little bit more detail. So we are going to find all theta between 0 and 2 pi, such that sine 2 theta minus cosine theta equals 0. So that is our mission if we choose to accept it. Of course we choose to accept it. Who wouldn't accept such a fun mathematical mission? And the key here, so the key is going to be the angle, the formula for sine of 2 theta. So sine of 2 theta is going to be 2 sine theta cosine theta. Okay? So this is the key. There's a similar formula for cosine of 2 theta. In fact, let me write it out because this one, it actually looks quite different. I shouldn't have said it's similar. Cosine of 2 theta is cosine squared theta minus sine squared theta. Okay. So this is neat. We don't really need it here, this cosine one, but it's good to go ahead and review that one as well. This is the one here that we're really going to need, this sine of 2 theta one. So if I plug this into my equation, then my original equation becomes 2 sine of theta cosine theta minus cosine theta equals 0. Okay, now I'm going to pause for a second and step aside again, because I think this looks a lot scarier than it actually is. If I asked you to solve 2x minus x equals 0, how would you go about doing that? Well, what I would do is I would say, actually, let me do it this way to make it, let's make it 2x squared minus x. Well, I notice that each of these have an x in them, and so I can pull an x out. I can factor out an x, right? Factor an x out. And now I know that x equals 0, or 2x minus 1 equals 0. And the second one, that's the same as x equals 1/2. Why am I doing this? What the heck, Bailey? You're wasting time. How is this related to what we're doing? We're doing trigonometry. Ah, yes, you are right. However, check this out. Even though cosine, this looks scarier because it's trig functions, but just like I factored an x out here, I can factor a cosine out here because both of these factors have a cosine, right? I've got cosine and cosine. And so my equation is now cosine theta. I can factor that cosine out, and I'm left with 2 sine theta, right? Because I'm left with that there, minus 1 equals 0. And just like we said about x a second ago, this means that cosine theta equals 0, or 2 sine theta minus 1 equals 0. Okay, well, cosine theta equals 0. So cosine of theta is 0 at pi over 2 and 3 pi over 2. And this second equation, 2 sine theta minus 1 equals 0, well, that means 2 sine theta equals 1, i.e. sine theta equals 1/2. And this is true at theta equals pi over 6 and 5 pi over 6. So we have these 4 theta values which satisfy our equation. The great thing about math is we can always check our work. So I encourage you, go ahead, plug pi over 2, plug all of these values, or at least 1 or 2 to check yourself. If you plug these values into our original here, you will indeed find that the equation is satisfied. Okay, so again, the key here is we use this trig substitution for sine of 2 theta. and we can factor just like we would normally factor with variables. It looks scarier because it's trig, but it works exactly the same. Okay, so I think that's all for now. If anybody has any questions about all of this, about anything here, please let me know via email. Drop a like in the, share it in the, share your questions in the comments. Drop a like, follow, subscribe, whatever. I don't know what people say at the end of YouTube videos. But I'm going to go ahead and post this as soon as I can and get started on the next video. So I'll see you guys tomorrow for sections. What sections is it tomorrow? I don't remember off the top of my head. I think 4 and 5. Math 140. Yeah, I will see you tomorrow for sections 1.5 and 1.6. Let me know if you have any questions. Take care, guys.